Let's see. Hi, I'm Kyle. I work at Development Seed, and I'm happy to be here. I will be talking today about cloud storage operations with Obstore, a recently new library that I wrote for Python. Historically in Python, if you wanted to work with agnostically with AWS S3, Google Cloud Storage, Azure Storage, you would have to have your own abstraction layers if you wanted to work with the vendor-supplied APIs. So Boto 3 provided by S3, Google Cloud Storage, each of those. If you wanted to have something that you could potentially move from cloud to cloud, you'd have to make some sort of abstraction yourself. There's been this library called FSSpec that has provided some sorts of abstractions across different backends, and FSSpec has been around, I think, almost 10 years, and is pretty widely used, but has some pros and cons that we'll see, and Obstore was designed to mitigate some of the perceived cons of FSSpec. So I really wanted to look at how Obstore and FSSpec relate to see where each of them might be better or worse. So FSSpec and Obstore both support a bunch of different backends. Both Obstore is really focused on S3 and S3 compatible providers like Cloudflare, R2, also Google Cloud, Azure, and local file system. FSSpec supports that and a bunch of other, a little bit more particular file systems or file system-like backends, so stuff like GitHub Files, Google Drive, but Obstore is really focused on cloud storage backends, and so it has a smaller scope that makes it a little bit easier to maintain. That's a bit where the commonalities end between Obstore and FSSpec. FSSpec really treats the API that it exposes to users as files, whereas Obstore tries to expose something like HTTP requests. And so the thing is, FSSpec really has this mismatched abstraction because object stores are not inherently file systems. You have to make an asynchronous request under the hood to access data on an object store. And so in the Obstore case, you get atomic operations, and you don't have hidden state under the hood. And so FSSpec, because it's stateful, sometimes it's a little bit hard to understand if you don't read the implementation carefully, what is actually happening under the hood with FSSpec compared to Obstore. And so here, these are code examples, FSSpec on the left and Obstore on the right, of opening an S3 bucket and listing it twice. And so with FSSpec, if you call ls twice with a sleep in between, what is actually happening? Is there one request or two? Is the request cached? What happens if the bucket changes between your requests? And in this case, FSSpec actually does cache the request. And so if anything changed, it won't be reflected in that second request automatically. You have to opt in to do that. Whereas Obstore is very predictable. Whenever you make a Python call, it immediately translates that Python call into an HTTP request. And so when you call list, that lists the bucket. And when you call list again, that always will immediately translate to that HTTP call. And so you know you are listing it a second time, and thus you get the current state of the bucket. Obstore has a much smaller API surface that makes it a lot easier to understand and compose and maintain. So FSSpec has this abstract file system class that has like 10 attributes, 56 methods. It's kind of hard for some users to understand when to use different parts of the FSSpec API. And it's also decently common to hit these not implemented errors because the API is so large that it's hard for all of the backends to implement the entire API. Whereas Obstore has a much smaller API surface that really focuses on just what is natively supported by each of these backends. And so that gives you this predictable performance and clarity of like what is actually happening with the HTTP calls under the hood. And also it has no automatic caching, though we have a layer that potentially is still in development, but you can use for some caching on top. And so here, this is the entire Obstore API. Copy, copies an object. All of these are verbs that are intended to directly match what is happening under the hood and be easy to understand. And so this is a lot easier, in my opinion, to really understand the scope of what's happening compared to FSPec. When you look at dependencies, FSPec is a Python base class and a Python API that then has other libraries on top, like S3FS, that depends on Boto3. Google GCSFS depends on the Google Cloud Storage library. And so there's a bunch of dependencies whenever you use an FSPec library. And sometimes you can have version conflicts. So sometimes the Boto3, AIO Boto Core, et cetera, versions can conflict, making it really hard to resolve an environment. Whereas Obstore has no Python dependencies because it relies on a Rust dependency that is compiled into Python. And so if you pip install Obstore, then it fetches a 2 megabyte wheel that is binary, and it'll always work without any question. It also means that the environment is smaller and faster to import. And so this underlying library is part of the Rust database community that I didn't have to build myself. It's an Apache project that is an open governance. And so this is just a Python binding to this existing widely supported project. Obstore also has full streaming support. And so because it doesn't try to emulate a file system, it can support some of these things that file systems don't support. And so Obstore lets you do streaming downloads, streaming uploads, and streaming lists that FSPec doesn't support really any of those natively. And so with a streaming download, you can iterate over the content of a file while still only making one request. Whereas with FSPec, if you iterate over a file, it makes new requests for each of those portions of the file that you're reading through. And with Obstore, we have both synchronous and asynchronous APIs. So if you're working with, say, a web server in Python that is asynchronous based, then it'll be a bit more performant in Obstore. Whereas FSPec does have some async support, but it's kind of bolted on because async didn't really exist in Python when FSPec was created. And this is intended to be pretty simple to use. So you create a store. In this case, this is a store that is pointing at a local file system. And you can just get a file and then iterate over that. And that gives you chunks of the object as bytes. This also then translates, ideally, as easily as possible, that between these two code samples, one, notice that we changed the store. So we went from a local file system to an S3 store. But the methods are exactly the same, no matter whether it's S3 or Google or a local file system. And then there's just 3 places that we change from the synchronous to the asynchronous counterparts. And now we have asynchronous iteration that doesn't block. So just changing from get to get async now returns an asynchronous response that then we can just use async for and will asynchronously iterate over the bytes of the object. We also allow streaming copy across stores. So in this case, this get async and put async just allows you to get a streaming download and connect that to the streaming upload into a different store. And so this allows, for example, if you wanted to copy objects from S3 to Google through some sort of proxy, this allows a very low memory overhead way to do this. Here, if, sorry, we love Slack. Here, this is the list implementation where just like downloading an object, it's intended to be kind of what's the most simple and predictable API. So list, that creates an iterator, and you can iterate either synchronously or asynchronously over the items in the bucket. Obstore also really focuses on type hinting as a way to, ideally, like you shouldn't even necessarily have to read the documentation to use the library accurately if you have type hinting enabled in your editor. And so when you create a store, this type hints all of the configuration parameters that you might need. So in the S3 case, it autofills the regions. In the top right, you can see these are a bunch of the different options that are allowed for you to pass in to the S3 store for configuration. And you can see the parameters, and then it'll autofill essentially the types that are allowed for each of those parameters. And so you get type checking as well. Here, skip signature expects a Boolean, and if you try to pass in some sort of string, it'll automatically error in your IDE saying, no, this should be a Boolean. Whereas in the FS spec case, they don't really have any type hinting, and so sometimes you're kind of left guessing whether you implemented the API correctly. And so that was in the step of creating a store. There's two steps. First, you create either an S3 store or whatever backend, and then you use that store for some operation. And so here, everything that can be typed is typed as well as possible. And so here, if you have these different HTTP options that you pass into the request, and that is suggested for you in your editor. Similarly with the result, if you're iterating over the response, or the response type is a buffer, or if you are listing a bucket, you see those are the items of the typed dictionary that are available for you in the list response. So there's a couple different ways to create a store object. It can infer from a URL, and so in this case, there is a top-level from URL function that you can pass an HTTPS URL, you can pass an S3 bucket path string, you can create the store manually with credentials. So in this case, you are passing in specific access key ID, secret access key, and here, this is the part that differs a little bit between the backends. So the S3 will have S3 specific implementation. Azure will have the Azure specific configuration. Obstore also really focuses on authentication as a way to simplify from earlier implementations. So Obstore allows you to pass in, well, first Obstore defines a bunch of native authentication implementations. So ideally, any way of connecting to S3 that you want to use, it should work out of the box. But then sometimes, if you want to do something special, you can pass in any arbitrary Python callback, and that will be called whenever you want to generate short-lived credentials for your session. And so in this case, we have a NASA Earth data credential provider that we provide out of the box from obstore.auth. The import is missing. And that implements this credential callback that allows you to access this NASA Earth data bucket that is an open data bucket, but you need short-lived credentials to connect to that bucket. And historically, it was really annoying to work with that data because the short-lived credentials would only be valid for an hour. And so if you had a long-lived process, you had to have code that would check, okay, have we gotten close to that hour? If we pass that hour, then my code will just stop working. Instead, this will automatically refresh your tokens for you by calling this callback that you provide before they expire. And so in this case, you don't have to think at all in your user code, is my token expiring? Has it already expired? It'll just work for you, even if your session lasts for 10 hours. I've also been working on connecting Obstore to a bunch of other tooling. And so in this case, we have Obstore connected to Czar. Big help from Max Jones, also from Development Seed, to get this over the line. And so this released in Czar v3.0.7. If you're not familiar, Czar is a project for serializing n-dimensional arrays to disk in a chunked cloud-native manner. And so Czar now supports this natively, and it's a very efficient way of accessing Czar, as we'll see in a little bit. Here, this is an example where it's a little verbose in terms of like the number of lines that are on the screen, but each of these lines are very, there's a different thing that each of these lines is specifically doing that fits together and composes very cleanly. So you really understand everything that's happening. First, we open up this stack client to see where in the planetary computer is this Czar data. Then we access, let's say we want the DayMet daily data set from the stack catalog, which is getting temperature data, I believe. And then we create this planetary computer credential provider. So if you've ever been wanted to use data on the planetary computer, been like, well, how do I access it? Then here, this handles all the authentication for you. Then you can pass that into an Azure store and then connect that to Czar and Xarray. And in just 10 lines of code, we fetched a lot of data and rendered this pretty image. We've done some benchmarking where this is loading large Czar data with Obstore, and we get up to 3 times better performance with Obstore than FSPec. This is happening partially because on the Obstore side, there's a multi-threaded Rust async executor. If you don't know what that means, you don't have to know what that means. But under the hood, away from the user, there's some of these performance improvements that use multiple cores where possible, so that if you are just wanting to get Czar data as fast as possible, Obstore may provide performance improvements for you. And so here we can also see with many requests to small files, we get higher throughput than even some of the most popular HTTP libraries in Python, like AIO HTTP, where AIO Boto 3 implements the special connection to S3 that is on top of an HTTP request, and that adds a lot of overhead, and we can get a lot better performance with only a little bit higher memory. So a couple of reasons why Obstore is faster, that it is particularly, like if you care about latency, that is only really determined by your network conditions. And so any library in Python isn't going to be able to get the first byte of data to you faster. But if you care about throughput and how well you can maximize the data that is traveling through the pipe to your computer, then potentially Obstore can be faster when you're CPU limited on how well you can use your network. This is a Python project, but if anybody's a Rust developer wanting to also expose this same API to their projects, there's a part of this project that is designed for other Rust Python projects that want to also support this object store access. So in case anybody's using Rust, they can look at that. On top of this, we've also been working on an async geotiff reader that has potentially much higher performance than raster IO. This is just for like maximum throughput for reading and reading cog data into memory. And so this isn't fully production. Well, some people are using it in production, so I can't say it's not production ready, but it doesn't have the user friendliness of raster IO. But if you are interested in async cog reading, then talk to us about this, and we'd love to co-develop or talk about some sort of work there. And Obstore has been getting a lot of improved downloads over the past 6 months, and so now it's up to 800,000 downloads a month. don't get 800,000 issues, so it must work for somebody. And thank you. We have a couple minutes for...
Yes, thank you, Kyle, for that very insightful presentation. Do we have any questions?
Great presentation, Kyle. Yeah. Thanks. I was wondering about data corruption, any validation in the Obstore that's handling that, making sure that the data that is passed through is, not corrupted.
There's some validation at the HTTP level to ensure that the data that is not corrupted via the HTTP process. I don't think there's any validation of what exists in the bucket, if that's what you mean. You would have to store checksums of your data separately if you want to know, is this data what I expect the data to be? But if you just are validating that the data wasn't corrupted in transit, then Obstore will handle that for you. Does that answer your question?
Just a quick question. Would we be able to access the slides somewhere?
Yes. I forgot to add a short link to the slides, but ask me for the slides, I guess. I don't know if I have a good place to say where they are. Oh, yeah. The talk will be online on YouTube.
No more questions. Okay, everyone, let's give Kyle a huge round of applause.